Okay, we are switching gears and talking about limits a little bit. This is basically the end of pre-calc, beginning of calc type stuff. So we're just getting a little taste of calculus before I get to pass you off to calculus. If you're going into stats, well, we don't really use the idea of limits too much, but it's still kind of fun. Okay, so today the video is going to be about how to find limits numerically and graphically, and then the next video will be about algebraically. That one might need to get split up into two videos, but we will go from there. This is really just a touch of limits. If you're going on to calc, I'm going to make a couple more videos for you for next week for you to watch, just to get an idea of derivatives a little bit. Mr. P said it would be okay, but I just want to give you a little bit of a heads up so that you're prepared and ready as much as you can be for calculus. Okay, so here's the definition of a limit. Basically, the idea of a limit is the number that f of x equals as x approaches a. So the way we would write this would be the limit as x approaches a of f of x equals L. So the limit as x approaches a of f of x, or well, I guess they say it backwards. The limit of f of x as x approaches a equals L. I usually say the limit as x approaches a of f of x is L. The idea is you don't have to necessarily equal a, but we want to know what f of x equals as you are getting closer and closer to a, but not equal to. So by using a table, well, I'm getting ahead of myself. Sorry. There's also this thing called one-sided limits. Think about asymptotes. As you approach an asymptotes, sometimes it's approaching one number from one side and a different number from the other side. So coming from the left, so as you start at the left side of a graph and move to the right, what is f of x approaching as you're coming from the left? That would be called the left-handed limit and the right-handed limit. And so the left-handed limit you have to be careful of and watch the small print because it's this negative sign right here, and sometimes it's really small on the paper. Well, I guess you're looking at a computer screen, but in general, you have to look out for that negative sign. And this is what shows you that it's a right-handed limit. And that's showing that you're coming from the right. So I will try to show you those as much as possible when we get to some examples that have different left and right-handed limits. One thing that will be exciting for some of you, and I'm sad we're not in class to do this, but a limit only exists for a number as long as the left-handed limit and the right-handed limit are equal to each other. So if it's approaching one number from the left and one number from the right, then it would not exist. So that's when the limit does not exist in Mean Girls. That's the whole the idea of a limit. We could watch Mean Girls, but well, we wouldn't really watch it if we were in class, if that makes you feel better. So if my A number was, for example, 2, and I had a hole there, or maybe it's a piecewise function. We'll be doing a lot of piecewise functions here. This limit would not exist because from the left, that would be coming this way. It approaches, let's say, -2. So the left-handed limit would equal -2. The right-handed limit would equal, let's say, 2. So this limit would not exist. And you would write does not exist for that limit because it's approaching two different numbers as you approach it from the left and from the right. For a limit to exist, it has to be basically a hole where from the left it's approaching a number and then there's a hole and then it's approaching the same number from the right, and from the left it's approaching that same number. Okay, so the first example is this one, the limit as x approaches 2 of this function, x squared plus x minus 6 over x minus 2. The first way I'm going to show you how to do this, it's a really basic idea. It's kind of like going back to graphing when you start with just plotting numbers, is to make a table of values and figure out what it approaches. So the idea is we want to get close. We don't want to equal to because, well, first of all, you can't even plug into here. So that would be a problem. So we want to get closer and closer to 2. So I usually plug in a couple numbers, 2.01, 2.001, and maybe 2.0001. The idea is we want to get closer and closer to 2 without actually equaling 2. Is it going to let me cancel out of here for a minute? Maybe. Keep, please. Okay. So to do this on our calculator a little bit faster, you can type that function into your calculator. We might have to split this one up into two as well. Okay. Make sure you have parentheses on the top. X squared plus X, I think that's what it was, minus 6, or was it minus? Let's go back and check. Nope, I was good. Divided by parentheses X minus 2. Okay, so granted, if we were to graph this, I'm not sure what my window is going to look like when I graph this. It would look like a straight line because there's a hole in this graph right at 2. So that this would be looking at it graphically, but if I want to just plug in numbers, I can type in 2.01. No, let's see. Sorry. I need to hit calculate first. And I want to find a value. There's a trickier way to get to that. I don't remember what it is though. 2.01. And we can see that that's 5.01. If we plug in 2.001, you can see there's 5.001. And you would plug in 2.0001, and it's 5.0001. From the graph, you can see that it's approaching the same number, but if we were just doing this numerically, if we just had a table, we would also want to try from the left-hand side too. So we would try 1.9 and see that it's 4.9. We try 1.99 and see that it's 4.99 and 1.999, and we would see that that was not 1.999. I think you see the pattern by now. 4.999. So the limit would equal 5. So let me just fill in these numbers. This was 5. Oh, come on. This was 5.01, 5.001. You can see numerically from the table, and then sometimes people write a double line here, and then that would be 4.9. You can see from the table that this is approaching 5 from both directions. And so the limit you would write is equal to 5. That would be your answer for this problem. It's a little sloppy, but you get the idea. I do know on Delta Math, they're not going to give you the function. They're just going to give you, you're going to plug in an X value and it's going to tell you the f of X value. So you have to figure it out. It's not going to give you that limit part. So you're going to have to use that table idea to figure out the numbers without the function. Same idea with this one. The limit as X approaches 0 of tangent of 3X over X. We're going to get numbers close to 0 from both directions. So we would want to get close to 0. We'd do like 0.1, 0.01, 0.001. And then we'd also need to go from the left side. So these would all be the right-sided limit if we were to do it left and right. Coming from the left would be the numbers closest to it. So negative 0.9, negative 0.09, and negative 0.009. Is that what I want? Do I want ones? I guess I could do ones too. Negative, let's start that over. Would it really matter? The idea is that you're really getting close to 0. So we could plug in our function again and get these numbers. You don't have, you could use this on the regular screen like this. Well, that's not it, but you can type in the tangent of 3x here. I just find it easier if I'm going to plug in a whole bunch of values to use the calculator to my advantage and do tangent of 3x divided by x. Let's see, I have my calculator in degree mode. Not that it really matters because we're just trying to get closer and closer to 0. We're not in the Zoom Trig phone. Let's go to Zoom Trig just so we have a nice pretty picture of it. My computer was not really feeling like working today, but I'm forcing it to work. Even then, this one's a little goofy. It does appear like it's approaching the same number. So if we go to calculate, so hit second trace, the very first one is value. So type in 0.1. you get 0.05. Type in 0.01, you get 0.05. Let's try 0.0001. You get 0.05. So let's try it from the other way, negative 0.1. I didn't like that. Why didn't I like my negative? Oh, because I didn't type in negative. I typed in a subtraction sign. That's why. So this one's kind of hard to tell as to whether it's approaching 0 or if it's approaching 0.5. Let's plug in a bunch of zeros here. When I typed it in my calculator, it looked like it was approaching 0, but this one does not look like it's approaching 0. We can also look at our table. Well, obviously there's an error. We'd have to change our table set to something different. I think I can just hit plus to change my table to like 0.001s and look right around 0. Hopefully 0 doesn't. It really looks like it's approaching 0.05236. So if I'm not going to fill in this whole entire chart, but it really looks like this is not approaching 0. It looks like it's approaching 0.05236. So that's an approximation. I don't think we could get any closer to that just using a table. Okay, this is really important. Really, really important is to understand this idea of this graph. I know these numbers are small, but to understand the difference of where a function equals a number as opposed to what is the limit. So I'm going to go in order of these first. Let's see if I can draw a nice pretty line. And I'm going to do A, B, C, D just like they're in order. So f of negative 4 is right here. Notice how there's no filled in point at f of negative 4. So that does not exist. There's no point there, so it does not exist. There's not a number there. However, as you're approaching negative 4 from the left, so that means coming from the left, you're getting closer and closer to it. You are approaching 2. So the limit is different than where the function equals a number. So the function does not equal anything at negative 4. There's a hole there, but the limit does exist. So from the right, it is also approaching 2. Remember what I said earlier is if the left-handed limit and the right-handed limit both equal the same number, then the limit itself exists and it's also 2. Let's look at f of f of 1. So I'm going to do this second row of problems right here. F of 1 is where the filled in point is. That's f of 1. And it equals 4. Okay, that's different than the limit sometimes. So let me change colors here just to make sure I don't get these mixed in with the other ones. As you're approaching it, this letter F, the limit as x approaches 1 from the left means start at the left of your graph, so over here, and we are going to start going to it from the left, and it's approaching 4. From the right, however, it's approaching, oh, that's a great arrow, it's approaching negative 2. Since these two numbers, 4 and negative 2, are not equal, then this limit does not exist. The limit has to be equal on both sides in order for it to exist. Okay, the third point over here is f of 6. F of 6 is the filled in point. It is referring to this point. Let me change colors again. I might as well erase that while I'm here. How about blue? So f of 6 is referring to that point. So f of 6 is equal to 2. The limit, however, when you approach it from the left is going here, is equal to 5. As you're approaching it from the right, it's also equal to 5. So the limit, since these two numbers are both equal, the limit is equal to 5, even though the ordered pair. Notice these are different numbers and they're allowed to be different numbers because the limit is where is it approaching. The function is actually where does it equal at that specific point. Those can be different. The biggest place where these can be different is piecewise functions. This is like 3 or 4 different pieces of a function, maybe 2 pieces plus a hole, 2 holes. But you just have to watch out. The function and the limit can be equal to different numbers. Okay, last example is a piecewise function, just to get the idea. We could graph this and see. I think it's visually easier to see graphing, but I do want you to think numerically as well. Notice this is two different pieces. I'll just stick with the blue. So as you're plugging it in, we're still going to do the idea of plugging in numbers. But as we plug in numbers closer to 3 on the left-hand side, so 2.9, we're getting closer, 2.99 and 2.999. I don't think I'll need a calculator for these. If we're plugging in 2.9, we're going to use this top function. So if I plug in 2.9, we get 10.9, 10.99, and 10.999. So it looks like the left-handed limit, let's see if we can write this right. X approaches 3 from the left. Notice the 3 is, oh my gosh, it doesn't like it when I do that. Of f of x, make sure you put the f of x because it's like, what are you talking about? That's kind of like the same as plugging in when I say write a function, put f of x, the f of x needs to be there. So the limit as x approaches 3 from the left is 11. So as we approach it from the right, let's see what it equals. 3.1, 3.01, and 3.001. I have my calculator here so I don't have to switch back and forth. 3 times 3.1 squared is equal to 19.22. Let's try 3.01 squared times 2. That is equal to 18.1202. And then let's try 2 times 3.001 squared. And that's 18.012002. Looks like this one's approaching. I try to plug in a few more numbers just to make sure. But this one from the right looks like you are approaching 18. Whoops, I did exactly what I told you not to do. Make sure you put the function there. The limit as x approaches 3 from the right is 18. Since these two limits are not exactly equal, this one's 11, this one's 18. So this overall limit as x approaches 3 does not exist. They are approaching different numbers from each direction. Okay. Tomorrow, well, maybe tomorrow for me. Maybe you're just going to keep going. We will talk about how to do this algebraically if you don't want to have to keep plugging in numbers. Plugging in numbers is always allowed. You just have to plug in numbers. It gets a little tedious. There are algebraic ways to figure out these limits without having to go through all that work every single time.